Bienvenidos, Ushamdid, and welcome UMGC learners from the CMIT-455 6380 course, which is the Cisco Networking Academy's CCNP ENCOR version 8 curriculum. And this is for the spring 2021 semester. In this supplemental video tutorial, we're going to be expanding on the information and the knowledge that we've acquired through Packet Tracer Activity 5.2.2 to take a deep dive look at the Link Aggregation Control Protocol. In fact, we're going to be creating a 16-member port channel bundle, and then we are going to go into the deep end of the pool where I'm going to show you how to change the port channel load balancing algorithm from the default, at least on the 2960s we'll be working with, which is source MAC address, and we're going to change it to one of the hashing algorithms that's going to load balance based off an exclusive OR, or the XOR operation. So it could be source and destination IP, it could be source and destination MAC address. And then we'll see what other load balancing algorithms the 2960 supports. And finally, I'm going to show you how to test, and we're going to put together a quick table that will conclusively determine over which member link in the LACP port channel bundle traffic will transit and in which direction based on that source and destination IP. So first things first, let's jump on to these two physical 2960s. Again, these are two physical switches that I have in my lab here in the Evil Command Center, and they have 16 Ethernet cables run between the two of them on ports Fast Ethernet 09 all the way to Fast Ethernet 024. Now, we're on switch 1 here, and switch 1 is not our root bridge. However, if I was to say show spanning tree, we can see what happens here when you simply take 16 cables and plug them between two different switches without configuring a port channel. And what you should notice immediately is that we have one port, Fast Ethernet 09, which is our root port, which faces and is closest to the root bridge, which is obviously in this scenario switch 2, and that is the only port between the two switches. Fast Ethernet 01, we have a host hooked up here. There's a MacBook that's hooked up here, but between the two switches, these 16 ports here, there is one port that is forwarding, and what are all of the other ports doing? They're blocking. Exactly. And so here's the use case for port channeling. We're using either LACP or PAGP. Now, I have gone into environments from a consulting perspective, and I actually will give you one use case or one scenario that I walked into, and that was we had a network engineer who was complaining about performance issues and, of course, was blaming it on the hardware. And what that engineer had done was he had done something similar to what I'm showing you right here, but he did it with 4 links. And what he was saying was, I've added, and these were all gigabit Ethernet ports. He says, I've added 3 gigabits per second by adding these 3 additional ports between the two switches, but I'm not seeing any performance improvement. And so the first thing we did was we got onto the switch and I said, show spanning tree. And this is exactly what we saw, was one of the ports was passing traffic. The other 3 were in a blocking state. And so his misperception of what would happen by simply plugging additional links in didn't necessarily address the problem that he was having. Now, the other scenario that I've walked into, and I believe it was either 2 or 4 links, and so we'll just say that it was with 4, but we had a user who had a PC over here, and we'll just say this is PCA or whatever, and they had another server over here, I think it was the web server, and they had created an ether channel right? They had created a port channel between the two switches, and they had left the default load balancing algorithm, which is going to be source MAC. And I'm going to show you how to see that here in just a second. And they left it as source MAC. And I think they had other servers over here. But the problem was let me ask you this. How often does the source MAC of a NIC card change? Yeah, it doesn't, right? They just don't. So that 48-bit MAC address is globally unique. It's burned onto the NIC card in the PC or the server or whatever the case may be. And so with a default hashing algorithm of source MAC in play, this was going to pick the exact same link every time, because switch 2 would perform the hashing algorithm, decide which link or across which link that traffic would flow based on the source MAC. The source MAC is always the same, meaning traffic going in that direction from the PC is always going across the same link. Instead of choosing something like source and destination IP or source and destination MAC address, where we have a better possibility of having unique values that would spread the traffic out in a more fair fashion. And so the way we addressed it was exactly that. We changed it to source and destination IP because, again, it was going to multiple systems over here. And so that was one way that we were able to help a customer understand how port channeling works. Now, that's very important. Know that what is not happening, and this is another huge misunderstanding with learners as well as network engineers, is that if we're doing something like source MAC, you'll notice I said that the traffic going in this direction is going to be pinned to the same link because the source MAC doesn't change. So switch 2 hashes it, it's going over that link. What is not happening with port channeling is that flow or that conversation based on the load balancing algorithm. It's not sending some of the frames over that link and some of the frames over this link and some of the frames over that link and some of the frames over that link. It's not doing that. It's not spreading them out over those links for the same flow. It is picking a single link. And so this is where we're going to transition briefly to a conversation of bandwidth versus throughput. And there is a very subtle difference here. Bandwidth is the aggregate amount of bandwidth I've gotten. Remember, I said 3 here because we said we added 3 gigabit Ethernet ports. We have 4 total, right? So I'll go ahead and cross that out. So we have 4 gigabits per second of aggregate bandwidth available. That's the bandwidth that's available. But let me ask you this, based on the conversation we just had, if source MAC is the hashing algorithm on switch 2, what is the maximum amount of throughput and bandwidth available to the PC? Exactly. It's going to pin to a single link. So the maximum amount of bandwidth would be 1 gigabit per second. And theoretically, right, the throughput that it could achieve will also be 1 gigabit per second. Now, we're not going to talk about TCP overhead and the 75%. If we did, we could say, maybe 750 megabits per second, but we're not going to drive that far down that hole. So bandwidth is what bandwidth is available, and that's just adding up the links that we have here. Throughput is what am I actually able to achieve from the PC's perspective, because that PC is not going to get 4 gigabits per second of throughput. It's not going to happen, right? And that's a huge misunderstanding that learners have, especially, again, we're talking about this with the source MAC as the load balancing algorithm. So let me give you an example. Now, source MAC is not a bad thing. Here's an example where source MAC may work. In this case, with a single PC, that is not going to work, or it's not going to give us the distribution of traffic that we would like to see. So let's do this, 2, 3, 4. So here's switch 1, here's switch 2, and off over here, we have router 1. Now, on switch 1, if I've got all these PCs, and let's say that there's 100 PCs over here hanging off behind switch 1. Source MAC in this use case, and there's that word again, right? In the use case where I've got a whole bunch of PCs over here that will, by definition, have globally unique MAC addresses, Source MAC works great on switch 1 because these MAC addresses, theoretically, are going to be different, right? In terms of the hashing algorithm, the way it hashes and looks at them. They're going to be different. And so we have a better chance of equal distribution across our 4 port channel links, member links here. Now, what about source MAC on switch 2? Because traffic coming from router 1, and I don't mean to be beyond router 1 here, just where it started. So what about source MAC here? Does that make sense here? Obviously not, because the source MAC of router 1 is always going to be the MAC of router 1 for this, say gig 00, gig 01, whatever the case may be. The MAC address is not changing on the router. And so to say source MAC down here on switch 2 would pin traffic this direction to a single link. And so this is going to answer a couple questions you might have right now. On switch 2, maybe I should use source and destination IP, or I could say source and destination MAC, because now we're transitioning to a conversation about performing an exclusive OR, which is that XOR. And the XOR with the source and destination values is going to come back with a specific value, and based off that value, we would pick one of these links, and they refer to it, you'll hear it as a member link, but an index, right? The index. And the index is just simply what member link is the traffic going to come across. And so this answers another question for you as well that I hope you're thinking about. Well, do the load balancing algorithms have to match on both sides of the switches here? And the answer is absolutely not. Because here is the use case where you wouldn't want them to match. You want source MAC down here, possibly, or maybe source IP, right? Because we're going to have a variation in values that's going to result in a better distribution of the traffic across these links. However, up here, for traffic coming into switch 2 from router 1, we don't want source MAC because the source MAC is the source MAC. It's not going to change. We want something that's going to spice things up a bit, that's going to give us variability in the results that we receive from the hashing algorithm that's doing the load balancing and selecting the links across which traffic is going to travel. All right, so we've talked about a couple of use cases here. Now we're going to go ahead and accelerate things, and we're going to get into the discussion of what happens when you have 16 links. And so let's take a look here. We're on switch 1. Remember, I said show spanning tree, and this is what we saw. We saw that all 16 of these links, and again, I'm talking about 09 to 24. We know that 01 is a host, and the same thing on switch 2. Fast Ethernet 01 is going to be a host. But 09 through 24, these 16 links, only one of them is passing traffic. So here's what we want to do. We're going to go ahead and we're going to get an interface range, Fast Ethernet 09 to 24. Now, I'm not going to shut these down because we would see a whole bunch of messages. It's going to make things really messy. Again, good idea, good best practice, shut them down, do the configuration, then bring things up. So what am I going to be doing here? Well, I'm going to say switch port mode trunk. And then I'm going to say switch port no negotiate. And again, flipping it from an access port to a trunk port, we're going to end up with a whole bunch of messages, but we've got that logging synchronous, so we get the prompt right back on the command line. So I've configured all the ports as trunk ports. I've configured all the ports so that DTP, the dynamic trunking protocol, is not running because of the switch port no negotiate. So we're good on this side. And I'm actually going to do the port channel with LACP right now. Now remember, one of the major differences between LACP and PAGP is that LACP will allow you to have more than 8 ports in a port channel. Now, notice I didn't say more than 8 active ports. PAGP and LACP both max out in terms of active ports with 8. That is the maximum number of active ports you can have, 8. However, LACP allows you to basically stage hot standby ports so that if one of the ports fails one of the member ports in the port channel fails, LACP will simply grab a guy off the bench and say, get in there, you're ready to play. And then that port would simply make up the 8th port, the 8th member port in the port channel for LACP. So that way we don't drop, in our case here, fast Ethernet ports. So the total bandwidth we have an aggregate of 800 megabits a second here is what we're going to have. And so maybe we don't want that 8th port to fall out because that's going to unbalance the hashing and the load distribution that we might be able to achieve with an odd number of links. And there's another question you should be asking yourself. Can I have an odd number of links? You absolutely can have an odd number of links. Now, is that recommended? The answer is no. It should always be an even number of links, and it should be either 2, 4, or 8 to give yourself the best distribution, even distribution possible. And if you were to Google port channel load distribution 8 links, you'll find documents out there that show you that with 8 links, theoretically, 12.5% of the traffic should be going across each of those links, right? Because we're dividing 100 by 8, we get 12.5. 100 by 2, you get 50%, right? That's an easy one. 100 divided by 4, 25% of the traffic, again, theoretically should balance over those links, but it's all about the hashing algorithm that we're using, because that's really driving the variability in the result, especially when we're talking about the XOR, like source destination IP or source and destination MAC address. All right, so we've got this configured. Let's go ahead and say, channel group 1 mode active. And so what I've just done, we've created port channel 1 or PO1, and we've used LACP. Remember, it's a best practice. If you're creating a port channel, you're using LACP or PAGP, put them in their unconditional modes, meaning they're trying to form a port channel. So PAGP, desirable. LACP, active. We just did that here on this side. Now let's go ahead and move over to switch number 2 here, and let's knock that out as well. And you can see we've had some activity on 2 because of the changes we're making on 1. So interface, range, fast Ethernet 09 to 24, switch port mode, trunk, switch port no negotiate, and then we're going to say channel group 1 mode active. Now, there's another command I'm going to show you here, which is the channel protocol command. And I mentioned that before. Now, the channel protocol command is an interesting command because it sort of provides you a little bit of protection. Now, there's a major misunderstanding with this command, and that it can be used in some form or fashion with the static unconditional EtherChannel on mode. That is not what this command does. The channel protocol command, and let me go ahead and get that typed in here. The channel protocol command, you'll notice we have 2 choices. And I mean, by virtue of the name of the command, channel protocol should tell you that it's not about the unconditional static EtherChannel on mode, right? It's about a channeling protocol, which is either going to be LACP or PAGP. And what this command is going to do, it's going to provide you with a little bit of protection against possibly entering a command for another negotiation protocol, right? Another port channeling protocol. So if I was to say channel protocol LACP, and you'll notice that's it, channel protocol LACP, and let's look at do show run int fast Ethernet 09. And you can see switch port mode trunk, no negotiate, channel protocol LACP. And what this is going to protect me against here, and again, I've just applied that to all of the ports in this port channel, is that if I was to come in and mistakenly say, channel group 2 mode desirable, right? So we get this command rejected is already part of a channel with a different protocol enabled. Range command terminated because it failed on fast Ethernet 09. So if we take a look at 09, we can see that nothing changed. In fact, if we looked at 010, right, and so forth and so on, you'd see that nothing changes. So that's really all that channel protocol does. But why not throw it in there to provide yourself a little bit of protection anyway against a typo or a junior engineer maybe going in there not understanding the change that they're getting ready to make. All right, so what should we have right now? Let's say show EtherChannel summary, because we should have a port channel configured between switch 1 and switch 2. And we do. And take a look at that. All 16 ports are recognized by this LACP port channel. However, remember, S for switch, meaning a layer 2 port channel. U, meaning it is in use. It is up. Think of U as up. The protocol is LACP. We have a capital P, right? It is bundled in the port channel. So this port is in the port channel. H, hot standby. And I alluded to this in the previous video, that this is what you will see for these hot standby ports. Now, you might be asking yourself, hold on a second, when in the world would I ever dedicate 16 links into a port channel with LACP between 2 devices? This seems like complete overkill. Remember, it's all about the use case. And so then you might be asking, well, have you ever done this? Have you seen this? Yes. So we were working with and I can't say who it is, but it was a group, military group, and they had 10 gig interfaces running between multiple devices in an LACP ether channel, and all of the port channels were 16 10 gig ports because they needed every bit of bandwidth that was running across that port channel. And they could not, for any reason, not have 8 active member ports in the port channel at any time. They needed it maxed out, and they needed maximum redundancy, which, as you can see, this clearly provides. And remember, if you're on a multi-chassis switch, what I mean by that is right now I'm using a pizza box switch, right? It's a small 48-port switch. But if you're on a chassis like a 6500, and again, those are kind of end of life, end of sale, so we'll say a 6800. 6800, where you've got line cards, and each of these line cards has 48 ports. What you can do, and let me set this up here, and let's say this is supervisor 2 and this is obviously not to scale and certainly not representative of what a 6800 looks like. But again, what I'm trying to explain here is that how would we do 16 10 gig ports? Well, we take 4 10 gig ports off of here and connect them to the other switch, 4 off of here, 4 off of here, and 4 off of here. And again, we've got this other switch over here that then goes to upstream somewhere. And there are the 16 10 gig ports. And talk about redundancy. Not only do we have 16 ports, but only 4 of them are on a single line card, meaning this line card explodes. Well, that's okay, because I've still got 12 possible ports up here, which means 8 would be live and 4 would be hot standby. And then what if this guy explodes? Well, that's okay, because I'm still running with 8 active ports in that port channel. And again, it's all about the use case. What problem are you trying to solve? What are you trying to do? All right, so we've got our 16 ports, and now we're going to go into the deep end of the pool, because the question now becomes, on the 2960, what is the default load balancing mechanism? So we'll say show EtherChannel load balance. This is how you see what the default load balancing configuration is. And as I indicated with the 2960, and this is basically I've seen this on every 2960, it's source MAC address, right? Well, what if I wanted to change that? Because I need something better. Again, we're assuming here, I need something better than source MAC. That is not going to get it done because we've only got one host on either side of the connection here for whatever reason, or I want a better opportunity for an exclusive OR to be done on a source and destination, either MAC or IP. Well, let's go ahead and say, EtherChannel, or not EtherChannel, port channel load balance. And again, you can see this is why there's so much confusion around EtherChannel, because we're told that it's called a port channel, and that's typically what's used. But then you see EtherChannel used in the commands, but then this command, it's not EtherChannel load balance, it's port channel load balance, right? And so this kind of causes a little bit of confusion, but again, you'll get used to it after a while. So I'm going to say port channel load balance, and on the 2960, this is what's supported. Not a whole lot. If you go on to a 6800, you go on to some of these bigger core switches, you're going to see source and destination IP and source and destination ports, right? And I mean, that gives you a great distribution, right? Because you've got a lot of variability there on which the hashing algorithm can perform the hash and select a port. And chances are, if you're looking at source and destination IP and source and destination port number, you should come up with some pretty unique values to give you a good distribution of your traffic across that port channel. 2960, not so much, but you see right here, we're going to do the exclusive OR, we're going to use the IP. And so to change this, source and destination IP. So port channel load balance, source destination IP. How would I confirm that? I can simply say do show EtherChannel load balance. And it's now changed. And here is how it's going to be working. It's going to be doing an exclusive OR, and that's where we're going to be going in just 1 second, because I'm going to come over here to switch number 1, and we're going to do the same thing. So we're going to exit out of here. Let's say do show EtherChannel summary, just to make sure that the EtherChannel is up and operational, and you can see that it is. Now let's go ahead and say, port channel load balance, and we're going to do what? Source and destination IP. And you can see this is another 29. They're identical 2960s. And so it's got the exact same configuration options available. So source and destination IP. All right. So we're at a good spot where I'm going to save the configuration of both of these guys in case for whatever reason we have a brownout here. So we'll say write mem. And it'll be on switch 1 where we're going to talk about creating this table. Because now learners typically want to know, well, how do I know across which link my traffic is going to go? And the answer to that question is it depends, because we're doing an exclusive OR on the source IP and the destination IP. And it's that operation, the exclusive OR, that is going to provide me with one of these 8 combinations of values here. Remember, we have 8 links. So what's going to happen here is we're going to examine the switch, I should say, is going to do an exclusive OR on the binary representation of the last octet in the IP address. And the result of that exclusive OR, which would be one of these 8 results right over here, 000, 001, 010, this is how the switch will decide across which member link that traffic based on source and destination IP. And you can see I've got source destination going all the way down here. And we're going to walk through each of these. And I'm going to show you how the switch makes that decision. All right, so here's the exclusive OR operation. If it's 00 for the exclusive OR, you get a 0. If it's 01 or 10, we get a 1. And if it's 11, we get a 0. So I can easily back my way in to this result. I can reverse engineer how I get a result where the 3-bit combo is going to be 000 for the last 3 bits after an exclusive OR. Here's how you would do that. If the binary representation, so the source IP, let's say it's going to be 192.168.37.32. 32 in binary would be 0, 0, 1, 0, 0, 0, 0, 0. And then let's say that this IP is 209.165.99.64. What is the last octet look like in binary? Well, 64, again, it's easy, right? This is kind of low-hanging fruit on these. And then 0, 0, 0, 0. And so these last 3 bits, because we're using an 8-member port channel. If it was a 4-member port channel, and I'll put that up here, if it was a 4-member port channel, I'd only be interested in the last 2 bits. If it was a 2-member port channel, I would only be interested in the last bit. And so here's what we look at. And this is what we do the exclusive OR against right here. So 0, 0, 0, 0, 0. Again, you know, this is kind of elementary here, but it's to show you this is how that's how we sort it out. So if the last octet in the source and destination IPs was .32 and .64 respectively, we break them into binary, we do the exclusive OR against the last 3 bits because we're in an 8-member port channel, we end up with 0, 0, 0. Now we come over here to our table of which port that traffic would transit. So to do that, we have to test. And this, I better be careful, don't want to erase this right here. So here's how we test it. And it's so easy. And this is one of the greatest commands ever, especially when we're talking about testing EtherChannel. I would say test EtherChannel load balance. Now, which interface? Well, we used interface P01. Now, is it going to be IP? Is it going to be the MAC? Is it going to be IPv6, right? We have to tell the algorithm, the hashing algorithm, what it is we're using to perform the hash. So we say IP. Now it's going to be the source IP followed by the destination IP. So I think I said my source is 192.168. And again, this third octet, it doesn't matter, 234, right? It doesn't matter what's in there because we're focused on the last octet and specifically the last 3 bits that we use to perform the exclusive OR. So I think I said 32. Was that what I said? I'm trying to remember if I said 32. Yeah, 32. And then the destination IP, 209.165, we'll do 73. Again, doesn't matter about the first 3 octets. The last octet's what I'm interested in, 64. Do a question mark and you'll see that's it. So it's test EtherChannel, load balance, interface P01, source IP, destination IP. You hit enter. That is the port that switch 1 is going, the member port that switch 1 will send traffic from these 2 IP addresses, right? From the source of 32 to the destination of 64 here. That is the port that would be chosen, Fast Ethernet 16. So let's go ahead and do this. Let's fill that in right over here. And we have the port. So we know that if the exclusive OR hashes to 000 in the last 3 bits between the last octet in the IP, when it's put into binary, it's going to choose Fast Ethernet 0, and I am sorry, I just thought 15, 16. It is 16. Okay, I'm glad I looked. Fast Ethernet 0, 16. All right, so that's that. So let's take a look here. Again, we can reverse engineer our way into this. So, and I'm not going to write the whole IP out, but if it's 128, what does that look like in binary? Well, that's easy. It's 1, 0, 0, 0, 0, 0, 0, 0. Because again, I'm trying to force this as the result, 0, 0, 1. 129. We take a look at 129. It's 128 and then 0, 0, 0, 0, 0, 0, 1. And we do our exclusive OR here and we get 0, 0, 1. And so therefore, that for traffic with a source IP of 128, the last octet, and in the last octet of 129, and again, it could be other values. These are not the only values where this is going to hash out like this, right? These are just the values I chose to try to keep it simple. So that's what it hashes out to. So let's see what member link we're going to be going across with a source of 128 and a destination, of 129. And I'll, pull that back up. We'll say 129, and I'll come over here and we'll say 128. 128. And we're going to choose Fast Ethernet 011. So we can come back over here and we can see that that's going to come across Fast Ethernet 011. Now, I'm not going to go ahead and do all the binary. So you should kind of get the idea. Well, let's do one more just so that you get the idea. So .5, right? So we have 0, 0, 0, 0, and then it's 8, 4, 2, 1. So this is 5 in binary. And then if the last octet's .7, 0, 0, 0, that's a value of 8. Boom, boom, boom. 4 plus 2 plus 1. I'm interested in these last 3 bits. And let's do our exclusive OR. 1 and 1 is 0. 1, 0, 1. 1, 1, 0. And so you can see we've got different values here, but we end up with that hash 0, 1, 0 with our exclusive OR, and what port will .5 and .7 transit over. So we just hit the up arrow and we say 7, and then we'll come over here and we'll say 5. And that would go across the first member link in our port channel, Fast Ethernet 09. So we can come back up here and we'll say Fast Ethernet 09. Now I've written these values down on a little piece of paper next to me, the .4726, the last octet. So we're going to go ahead and we're going to rip through these last combinations, and then we'll come back and fill this in here because we know that those are going to match. And then I'm going to ask the question, isn't there a command that I could run that would show me the indexes? And the answer is yes, there is. And let me get to that because, again, we're on a lower end switch here. And so the 2960, at least the model that I have and that I'm using, is not going to be of much help to us in that instance, and I'll show you what I mean there. So next, let's take a look at, we did 5 and 7, so let's do, let's leave it at 7. We'll do 4 and 7. And you can see, and let me write that down so we'll keep track of these, and that's going to be Fast Ethernet 014 for 4 and 7. And then we'll do 2 and 6. So I say 6, and we'll come over here and we'll do 2. And that's going to be Fast Ethernet 13 or 013. Let's do 3 and 6. And hopefully you're getting the feel and you're feeling confident here that you could, with the exclusive OR, and again, it would be the same thing with the source destination MAC, it's just that you would have to convert that hex to binary and get to those last 3 bits in order to sort this out. So 3 and 6, and then we'll do 4 and 2. And you can see that goes over Fast Ethernet 012. And then finally, we've got 3 and 4. And again, these IPs that I'm using, these last octet values, are simply just sort of pre-canned in order to generate a certain specific result. All right, so we've got our values there. Let's go back over here and let's fill those in and let's see what we've got. So 011 was Fast Ethernet 014. And that is a very bad 0 right there. Hold on. 014. 100 was Fast Ethernet 013. And we know what the result of this is going to be, what the result of that is going to be, because we've already computed it there based on the values that we had. 010. And then 110 is going to be Fast Ethernet 012. And then finally, this guy, 111, if this is the XOR result, is going to go over Fast Ethernet 015. And so take a look at that. 9, 10, 11, 12, 13, 14, 15, 16. All 16 ports, all 8 possible 3-bit combinations, not a single one of those goes over, or I shouldn't say, not a single pair of those is using the same port. And that's the exclusive OR. And this is how, by hand, you could check that out. And more importantly, if you're curious about that, and you wanted to know based off of your load balancing algorithm what port that traffic might be going over, because you want to see, hey, am I doing a good job here? Am I providing enough variability in my load balancing algorithm to spread that output across these links? That's exactly how you could do it. Just use the test command. It's a great command, right? A great command. And you can see if we go all the way back to the beginning here, test EtherChannel load balance interface, whatever the port channel is. And again, we're using source and destination IP. That's why we've got IP in there, and then the source IP and the destination IP. Now, you might be wondering, well, there's got to be a way to see that without doing this all by hand or running all of these tests, right? And the answer is that there is. So I'm going to say show EtherChannel 1 port channel, and I think it's port maybe, or no, here it is, port channel. So here's the command that you could run that's going to show you the load that each of these is currently experiencing, that each member link is currently experiencing. It shows you the EtherChannel state. It's going to show you the number of bits. And most importantly, here's this index field. Now, on the 2960, you get all zeros here. So if I'm looking at this, it's a little bit difficult for me to figure out in my head, well, is this index 1, 2, 3, 4, 5, 6, 7, 8, or is it 0 through 7, or what are these index values, right? And so with this output on this model switch, we get all zeros here. And on lower end switches, this is a possibility. On the higher end switches, you should receive a value in here. And you should have some kind of a load value. Again, obviously, if traffic is passing across those links, I think right now I might be running a ping command. And in fact, here's the ultimate test right now. I've got two MacBooks, one on switch 1, one on switch 2. They're all in VLAN 1, and everything we're doing is in VLAN 1. So they're running continuous pings against each other. And I know the source and destination IP addresses. So let's pull this back up. And again, I could leave the first 3 octets as anything I want, right? Because remember, we're only focused on the last 3 bits in the 4th octet's value. But I'll put the actual IPs in here. So it's 10.0.10.100 is the source on this side, and 10.0.10.101 is the source on the other side. And so what that says is traffic from this MacBook plugged into switch 1. And if I was to say show MAC address table, and let's include fast Ethernet 01, and you can see that's the MAC address of the host, and it's on fast Ethernet 01, and we're pinging across. If I say show interface fast Ethernet 01, I should see that we've got some traffic. And take a look at that. Yeah, we've got some packets, right? And again, these are just ping packets that are running here. And you can see that at least traffic is flowing. So if that's the case, that traffic is flowing, and if what I'm telling you is true, we should be able to say show interface fast Ethernet 011 again, this is in an operational huge enterprise environment. This is probably not going to be how you do it. But here, this will conclusively show you, do we have packets going across that link? And we do. And again, the reason you're seeing a difference in the packet count is because I was pinging, these switches have been up for a while, and I was using this prior. So we've got this output here showing that that is the link that is being used. In fact, let me do this. Let's see if it's increasing, right? Because maybe you're saying, well, no, that's a static number you're showing me. Is it increasing at all? And take a look. 16,091. Now it's 16,157. 170. 174, right? As the traffic is flowing from the PC with they're just ping packets that are going, but that shows you that it tells us what member port we're going across. And we can confirm that right here, right? So proving that that hashing algorithm and what it's telling us, that test command, is in fact correct. All right, well, that is going to do it for this deep dive into not only LACP, but more importantly, into port channeling, into the hashing algorithm, and then answering the question, how would we figure out what port my traffic is going across based on this source IP or this source MAC and that destination IP or that destination MAC? And this is really where, for the professional level engineer, you should be in terms of being able to troubleshoot layer 2 issues with port channels, the configuration of them, and then the monitoring and making sure that your traffic is evenly spread out. All right, well, that does it for this video. I really appreciate you watching. Hopefully this has given you a much better understanding of exactly what Cisco's load balancing algorithm is doing and how it's making its decisions in terms of which member link your traffic is going to cross, or transit for that matter. All right, guys, thank you so much for watching, and I hope to see you in the next video.